Project scheduling is a crucial aspect of project management that involves determining the start and finish times for each activity or task in a project, ensuring that the project meets its deadlines, stays within budget, and utilizes resources efficiently. In large-scale, resource-constrained, or time-sensitive projects, finding the optimal schedule can be computationally expensive or practically infeasible due to the complexity of the problem. This is where heuristics come into play. Heuristics are problem-solving methods that provide good enough solutions in a reasonable amount of time, especially for complex and large-scale problems like project scheduling problems, PSP. Understanding project scheduling problems. In a typical project scheduling problem, tasks or activities need to be arranged in a sequence that respects dependencies, optimizes the use of limited resources, and ensures the timely completion of the project. A project scheduling problem, PSP, can include various types, such as 1. Single project scheduling, managing the schedule of tasks for a single project. 2. Multi-project scheduling, managing the schedules for multiple interrelated projects. 3. Resource-constrained project scheduling problems, RCPSP, where the resources, e.g., labor, machinery, materials, are limited, and tasks must be scheduled efficiently within these constraints. 4. Time-cost trade-off problems, where project timelines and costs are balanced, such as deciding whether to shorten the project duration by increasing resources and costs. In all these scenarios, finding an optimal schedule involves considering multiple variables and constraints, including task dependencies, resource availability, and the desired project outcome. What are heuristics? Heuristics are simple, rule-of-thumb strategies or methods designed to solve problems faster than traditional algorithms by sacrificing optimality for speed. They do not guarantee the best solution but are often able to find good or near-optimal solutions within a reasonable amount of time. This is especially valuable when dealing with complex and large-scale problems that might take too long to solve using exact methods, e.g., branch and bound or dynamic programming. Types of heuristic methods in project scheduling. Several heuristic methods can be applied to project scheduling, each with its advantages and suitability depending on the complexity and nature of the project. 1. Priority scheduling rules. These are among the simplest heuristics and work by determining the order in which tasks should be performed based on priority criteria. Some common rules include 1. Shortest processing time, SPT, prioritizing tasks that require the least amount of time. 2. Earliest start time, EST, scheduling tasks that have the earliest possible start time first. 3. Longest path first, LPF, focusing on critical tasks that are crucial for project completion, often used in critical path scheduling. These priority rules are simple but effective in projects where tasks are relatively independent, and the resources are not severely constrained. 2. Greedy algorithms. A greedy algorithm is a heuristic where the schedule is built step by making the locally optimal choice at each stage. In the context of project scheduling, a greedy algorithm might select the task with the earliest start time or the task that can be completed using the fewest resources at that moment. For example, a greedy approach could select tasks based on the least resource requirement or minimal time, under the assumption that these decisions will lead to a globally optimal schedule. While this method does not always yield the best solution, it is often computationally efficient and provides a good starting point for more complex scheduling tasks. 3. Genetic algorithms, GA. Genetic algorithms are a form of meta-heuristic that draws inspiration from natural evolution. They are used to find approximate solutions to optimization problems by evolving a population of potential schedules over successive generations. In a genetic algorithm, the following processes are applied. 1. Selection. Selecting the best schedules based on a fitness function, e.g., shortest duration, best resource utilization. 2. Crossover. Combining two parent schedules to create one or more offspring schedules. 3. Mutation. Introducing small random changes to a schedule to explore new possibilities. Genetic algorithms are particularly useful for solving complex project scheduling problems with large numbers of variables and constraints, such as RCPSP, where other methods might be too slow or computationally expensive. 4. Simulated annealing, SAW. Simulated annealing is another meta-heuristic inspired by the process of annealing in metallurgy, where a material is slowly cooled to remove defects. In the scheduling context, it explores potential schedules by 1. Accepting worse solutions with a certain probability, to avoid local optima. 2. Gradually reducing the likelihood of accepting worse solutions over time, mimicking the cooling process. Simulated annealing is particularly useful for finding near-optimal solutions to complex scheduling problems with many variables, though it requires careful tuning of parameters to balance exploration and exploitation. 5. Tabu search. Tabu search is a local search heuristic that improves upon traditional methods by allowing the algorithm to escape local optima. It maintains a memory structure, called the tabu list, to track previously visited solutions and avoid revisiting them, thus enhancing the search process. This heuristic is suitable for large and complex PSPs, as it allows the algorithm to explore a broader set of possible schedules, leading to better solutions than greedy or simple local search methods. Advantages of using heuristics in project scheduling. 1. Time efficiency. Heuristics are faster than exact methods, making them ideal for large-scale projects where traditional optimization methods would be computationally expensive. 2. Simplicity. Heuristics are typically easy to implement and understand, making them accessible for project managers who need to make quick scheduling decisions. 3. Flexibility. Heuristic methods can be adapted to different types of scheduling problems, e.g., multi-project scheduling, resource-constrained problems. 4. Scalability. As the size of the project grows, e.g., more tasks, resources, or constraints, heuristics remain effective and do not suffer from the combinatorial explosion faced by exact methods. 5. Robustness. Heuristics can handle uncertainties or unforeseen changes, such as resource shortages or task delays, by adjusting the schedule in real time. Challenges of using heuristics in project scheduling. 1. Suboptimal solutions. Heuristics do not guarantee the optimal solution. 1. They provide good solutions in a reasonable time but might miss the global optimum. 2. Lack of precision. In some highly critical projects, e.g., time-sensitive or safety-critical projects, the lack of precision might not be acceptable, and exact optimization methods might be preferred. 3. Parameter sensitivity. Some heuristics, like genetic algorithms or simulated annealing, require careful tuning of parameters, e.g., mutation rates or temperature schedules, which can be time-consuming and difficult to manage. Real-world application of heuristics in project scheduling. Consider a real-life scenario where a construction company is tasked with building a skyscraper. The project has numerous tasks, excavation, structural work, electrical installations, etc., that are constrained by limited resources such as workers, equipment, and materials. Using heuristic methods, the project manager could 1. Apply priority rules to quickly assign tasks and begin work on the most urgent activities. 2. Use a genetic algorithm to optimize the schedule, exploring a broad set of possible task orderings and resource allocations. 3. Implement simulated annealing to fine-tune the schedule over time, making incremental improvements while avoiding local optima. Through this approach, the company can ensure efficient resource use, meet deadlines, and stay within budget, even if the optimal solution is not always achievable. Conclusion: heuristics play a critical role in solving complex project scheduling problems, especially when the number of tasks, dependencies, and constraints makes traditional optimization methods impractical. While they do not guarantee the best solution, heuristics provide fast, flexible, and efficient means of generating good enough schedules for large and complex projects. By using techniques like priority scheduling, greedy algorithms, genetic algorithms, simulated annealing, and tabu search, project managers can tackle scheduling challenges and make informed decisions that optimize project performance in real-world scenarios.